Hi, everyone. Welcome to my talk on Venice database as a service. So here's my agenda for today. I'm going to first cover my use case. So what kind of things I'm actually doing, and then I'm going to actually describe the Venice service high-level architecture. And after that, I'm going to dive into the schema and the query, see the good stuff. And also, I will summarize my talk with my conclusion why I end up using Postgres, kind of why I decided to use Postgres as a foundation for the OLAP service I'm building. So a little bit about me first. I've been working at Microsoft for quite a long time. For the past few years, my specialty has been doing OLAP, building various kind of OLAP systems, and doing the in-database machine learning. And to tackle the OLAP problem, I have used and investigated a lot of different technologies like HiveQL, Spark, Flink, and all the way to some say arcane or exotic column store system like an APL family, like a KDB. For the past 2 years, I've been almost exclusively focusing on using parallel SQL-based system to build OLAP solutions. So here's my high-level use case. I work in the Measure platform team inside Microsoft. So one of our biggest customer is Windows engineering team. So effectively, we have to deal with lots of Windows telemetry data. So each Windows laptop, as you might be aware, is emitting thousands of events every day. Right? So once the events get transported to the cloud side, we actually using the complex event processing. It's a batch system to stitch the events together, to sectionize them, and to fabricate the thing we call a measure. Say, as an example, if you click on the start menu on the Windows such laptop, there at least 2 events get fired. One start menu click, and the other start menu launch. From those 2 events, we can fabricate a measure called start menu launch latency. And while we calculating the matrix value, we also enrich this matrix value with a lot of dimensions, because we know which build of Windows is actually running, and what's the hardware characteristics about this device, kind of using hard drive, SSD, and what's the processor family, and all that kind of stuff. So we have lots of a server side enrichment for the dimensions. As you can see that each Windows device could have up to thousands of measures, right? So from measure from a logon, from start menu launch latency, from Wi-Fi, and then we have monthly, I have 500 million active Windows 10 active devices. So effectively, we have tens of billions of rows for the database. And on the data consumption side, so once we store the measure inside the Venice cluster, there's 2 consumption. One is just as a normal run-of-the-mill kind of interactive ad hoc queries to the slice and dice according to different dimensions on a single measure basis. So another, let's say, usage pattern is group those measures actually together, become a dashboard. So as I speak right now, there's a meeting going on back in Seattle side. So the Windows ship room is actually looking at the Venice Power dashboard to make, quality decisions, right? So these kind of reflecting the weekly and monthly metrics for those measures. So here's a high-level architecture about the OLAP cluster. I would say this is a quite typical architecture. It consists of data integration queue, and it has a database cluster, and it's actually powered by the Citus extension. And then we have this API gateway for the dashboard integration. So I'm going to cover each of the major components in turn. I'll start with the database cluster. So VeniceDB it's a code name, right? It's not really like database, and I did not create a new like database technology. So it's a custom build of Postgres, and with extensions like a Citus, and a few other I call it smaller, but it's actually very important, like data types, like a hyperlog log, and I'm also using say the blooms and a few other custom data types. So there's a few characteristics about this like database cluster. First of all, it's very I/O intensive. It's ingest about terabytes of data daily, and due to the regulatory requirements, since we store the device ID, we have to delete equally amount of the data like every day, right? So from the OLTP point of view, it's almost like we to do the bulk ingestion and bulk delete. The database size, including index, is about 100 terabytes, and since it's a data warehouse, so the read I/O is very heavy. Every day we pull about 500 terabytes of the data out of the disk and try to serve the queries. And talking about query, constantly this cluster is packed with hundreds of database connections to serve thousands of concurrent queries. For the type of query we do, actually we're going to talk about in a second, it's actually quite expensive OLAP queries. And the P95 latency currently is less than 4 seconds, is actually quite impressive. And then I'm going to talk a few words about the database cluster itself. So Venice is built on top of Azure. I would actually think it's actually very hard to buy my own hardware to building a service cluster like a Venice. Because Azure has been evolved in such a way that it's giving me the capability to disaggregate the storage and compute. Well, that's why I can, on the slide, I say, hey, I need 700 cores, 4 terabytes of RAM, and 160 terabytes of disk, right? So, I mean, these disks are, it's called an Azure Premium disk, or sometimes I call it managed SSD. So it actually allow me to actually build effectively like modern like mainframe like database cluster. There's a few trade-offs I made. There is no database level replication, and I do not do the backup, so there's no point in time recovery. Well, then how do I handle the disasters, right? Because let's say the data corruption could happen, like due to say OS bug or the Postgres bug even sometimes. And so the idea is, since I partition the data in such a way that I can always recover the data by re-ingesting that particular portion of data being corrupted. So I think enough about the database cluster. I'll just come to dive into the schema a bit. So here's a simplified version of the measure schema. So I show this just to give me a basis to talk about the query afterwards. So it has a measure ID, because every query is say, okay, where to kind of say measure ID equal to like something. And as you can see, it has 2 timestamps. One is event timestamp when which set of events generate this measure, and the process time is when this measure is fabricated. And it also has a complex like data type, in like JSON, which is stored tens of, sometimes say hundreds of like dimensions. And there's 2 metric column. One is count, or call it, say cardinality on slice, and the other is value, and here I call it sum. So even for this simple table, it actually took me a while to figure out how to actually partition it. So, I mean, because I want to say that this table to partition evenly on all nodes on the same cluster. So after a few experiments, I finally decided to actually put the device ID. Well, this is actually a hash version, as MD5 hash version of the device ID. So as a partition key, and it's using the Citus like hash partitioning to the first level like partition. And then for each hash partition is further range partition. This is a Postgres 10 feature to be range partition by the process time. And I said, so the reason I kind of partition by the process time is for as a recovery, right? And is also for easier for the ingestion. As you look at this table, it's probably there not much we can do to actually serve query fast, right? Because at the end of the day, we're not just a storage, we're actually a database to serve queries. Turned out, there's a few tricks we can do. Most of the time, we actually know the
Do you also have the sharding key here or only the partition? Do you have the sharding key as well or only the partition keys?
Well, I think, well, I mean, it's control-level sharding, right? So the device ID is the partition key, and also I think that is called, like, say, like sharding key. Yeah. So as I said earlier, say the base measure table is not very efficient to serve queries, since we know a lot of common dimension sets for query patterns. So we actually have the concept of cooking this or pre-computing quite a bit of say a thing we call derived tables. So here's a template of the derived table. We had quite a few, probably by 10 derived table right now. As you can see, it had a device ID in there. And also, since all the query reporting is on, say, the event time, so I just get rid of, say, the process time. And then it has a few common dimensions depending on what the purpose this table is for. So the device ID, I just showed this say the Citus extension syntax, so allow this table to be co-located with the measure table. So this is actually crucial because this allows me to use a Postgres upsert, right? It's called insect select on conflict upsert to do the parallel processing on every node on a cluster quite evenly, right? So it's kind of like do it per partition per shard, kind of like parallel cooking. So, I mean, this to me is actually very exciting because given my other experience on the MapReduce, this is actually MapReduce. Okay, so now we cover the schema. So let's dive into query. The first, I'm going to talk about a lot of average calculations. So I've tried to corner all the average calculation in this talk. So first, okay, what's so special about average calculation, right? You can just say measure ID equal to 1, 2, 3, sum the sum, and sum the count, and let's say divide by them. Well, it turned out this kind of naive calculation were causing the average value to be skewed towards a certain device population. Say, take the start menu launch latency. And an old laptop with hard drive, take a few seconds for the start menu to show up. On a new laptop with SSD, probably a few milliseconds, right? So if you just do a naive calculation, then the average number will skew towards the old, slow laptops. And the engineering team actually does not like that. So turned out, so there's a way to mitigate this. This is what we call device-centric average calculation. So what it does is for each device, we calculate an average value, and then we average the average value, become this device-centric average value. So as you can see from the slides, this effectively is just two-level group bias. Let's just say for this measure, there's 1 million, say device IDs, and it's a 28-day data aggregation query. So the inner select query generate about 28 million data points, and the outer query collect them down into 28 data points. Okay, so next I'm going to cover is actually a percentile calculation. Turned out that because the data is being shared on a distributed cluster, so the built-in function of the Postgres percentile is not applicable anymore. well, turned out you can invent your own like percentile calculation algorithm. So I showed one example here. Sorry about this such busy slides. Basically, to do I call it approximate percentile calculation. It's kind of emulating in some other systems, like I say, a T-digest. So I would actually just hand wave about the high-level algorithm first to show what this tens of SQL statement actually does. So I still do the device average calculated, and so the next one is I bucket the average into a set of, weight and value pairs, right? Because quite often, right, because we have millions and 100 million of devices, a lot of the averages could belong to the same bucket. I mean, they have similar average values. So after you bucket it, then I use the SQL window function to calculate the prefix sum. So to getting the weight, and so a value pair aggregated horizontally. Once you've done that, once you have the prefix sum, you can almost slice into any percentile you want, right? It's going to have, in this particular case, it's a P50, but you can also get a P90 and things like that. So the other reason I show this query is about a year ago, after I realized I can implement a percentile calculation in SQL like this with Citus, I was sold on Citus actually, because this was a test. I said, okay, if I can do this, I can do a lot of other things, right? So I was actually very excited about this actually, I say about the Citus itself and about the whole validity about the Postgres ecosystem. Yeah. Oops. Yes, yes.
So the window function is operating on something that's local to the machine that it's on.
Yeah.
Would it be valid, or I would assume that it would work, but it would be slow if you tried a window function that was not partition bound?
Well, I think turned out actually. Oh, okay, sorry. Yeah, I think the question is about it's kind of whether the Windows function would actually do the calculation locally, right? Because if it's not, because event time is one of the partition keys. Well, it turned out what this does is because the width, the common table expression, is actually extracted all the data, so actually to the coordinator node. Right. Right. Yeah. I mean, because it's actually data. On the expensive query is actually inside, say, the common table expression, and then it's a smaller amount of data get pulled into the coordinator node. Yeah, I think the Citus actually does support, I think they call it push and pull model, and I call from my background, I call it iterative MapReduce. I mean, there's a few examples for that. I'm still trying to find some use case for it. Okay, so I'll come back to the average again. I think in the example I've given, I only talk about, give example about 1 million device for this measure. And what happens if, quite often in our case, is there's 200 million device IDs, right? And then aggregate over 28 days time window. We're talking about approximately 6 billion rows. And it's kind of to aggregate, I'd say about 70 gigabytes worth of data. Right? That's a lot of data to aggregate. So I tried with different kind of approach. I think on column store, row store, doesn't really make a material difference because it takes just minutes on the best commodity hardware you can actually calculate with this. Right. So I think the challenge is how can you do this kind of query under a second? And turned out there's a few special case for this. I'm going to explore one of the special case here. Basically, we call the failure rate investigation. So if you think about say the like 6 billion rows and look at the data, what kind of things you're looking at? So for the failure rate average calculation, let's say the fail signal is 1, the success signal or non-fail is actually 0. So if you look at the data, it's actually very sparse, right? I mean, there are only probably a few thousand, maybe even say a few actually million ones, but there are billions of actual zeros. So the first inclination is, can you compress the data, right? Because the data, I mean, from the mathematical point of view, the vector is so sparse. Well, it turned out you can. So if we back to the arithmetic, right? So what is average does? So average does is it has a numerator, it has a denominator. So the numerator is to calculate the failure signal, so which is all the ones are actually there. And then the denominator, which is the whole population. Turned out you can just using the hyperlog log actually like data type to pre-aggregate the total device like population, right? Because these are the most of the time is actually spending on. Because otherwise, if you look at the query, is aggregating a lot of actual zeros. Because like Postgres doesn't care if you sum zeros or sum ones, because I mean it's equally costly. Once you have done that, because calculating the numerator would take a second or less, and so calculating because you pre-aggregated hyperlog log has a capability, say, allow you to do the row ups. So that calculation is also under a second. So then the whole well, here's actually the solution to address the challenge about how do you can calculate the failure rate. I mean, for a retail population, right? Because this turned out to be a very important mechanism. So so first I did this, I was very excited about it. So I showed it to a few people. And then the next thing I know, the Windows engineering team just want hundreds of these kind of like say measures, because this would help them to calculate catch the rare failures against say or we call it retail population. So I say there are certain Wi-Fi kind of say the errors, right? That only occurred with a few device models or sparsely around the globe a bit. So if you use sampling, and you would lose all the signals, right? So because sampling is not effective. And I also want to actually call this is actually a use case to using an OLTP solution to solve an OLAP problem, right? So from my column store experience is yes, with column store, because segments are say immutable, you can pre-aggregate those hyperlog stuff into segments. Then you still need, since you cannot do updates, you still need to pay the cost of the query time merging, right? So I would say that using a pure column store-based solution would not meet this at 1 second like requirement. Okay, now I can cover enough about the database cluster. I want to just go over like briefly about the queue-based system. I think initially I actually used Kafka for this like integration queue. Why? Because I don't have to do any work, and this is what everyone else is actually using. And as I go into the production mode, I had to be very cognizant about the cost. Then I realized, since I'm in a cloud environment, I do not really need this Kafka queue and the Kafka storage. I can just using say the Azure blob storage, because if you think about what the blob storage does, I mean, it's actually a key value store. It's support key point lookup. It's also you can do the range like scan, because the value is just I could say like data blob itself. The key is just the timestamp. I mean, with say potential like file name or the say the data set's name, and the cost saving is actually incomparable, right? Because Azure blob storage, probably you may know that it's about $10,000 per petabyte per month. I would say like nothing like you can build would actually be this like a price. Well, since I replaced Kafka, it's kind of like then why stop there? And I had the initial ingestion code done by a small Spark cluster. Then I realized I can just replace with almost just a single process with Go. And I can just store the offsets inside the Postgres table itself, right? Because if Postgres cluster is done, my system is done anyway. So almost in one scoop, I just save 20% of the cost. So I would also cover a bit about the gateway. I just want to call out 2 points. First is we're using the Azure Redis cache service to do the result caching. This is pretty typical. I think another trick is for people probably implementing the executive decision dashboard is I call it concurrent query deduping. Because once you have thousands of queries coming in, quite often, say maybe even up to 100, they are effectively the identical queries. Right? You can either send 100 identical query to the Postgres cluster, or you just choose to send one once this query applies, and the other queries also being satisfied. Right? This turned out to be a huge win in terms of database resource utilization, because you can conserve the resource for other queries. Okay, so now I'm approaching the end of my talk here. So I was asked, okay, why pick Postgres, right? So it's it's actually bizarre to think about using Postgres to solve the OLAP problem. So I actually did not start with Postgres. I started with my OLAP cubing problem. Because we have a MapReduce cubing job just takes longer and longer, and thanks to the curse of dimensionality, quite often just running out of memory, so on some of the nodes. And my first inclination to solve the problem is, can I make cube generation faster? Right, so I was researching and doing all kinds of things, and I actually realized, hey, well, okay, so since my job is slow, can I make the job faster? So Flink can claim can make the job faster. So indeed, it can actually make the job faster than the system I'm actually using. So and there's also a very cool feature called queryable state. That was about say a year and a half ago. I was looking into this. And the queryable state in database world is almost like a table. Well, it turned out they have very limited SQL support, and there's no secondary indexing. I don't want to build my own say a database on top of that by myself. So in parallel, I actually worked a few months with linking and P-Node folks, right? So because linking is part of Microsoft. So P-Node is actually a tailor-made solution for OLAP cubing, right? So that's why I pick out to look at it. Turned out the P-Node has the core technology. They can do the iceberg queries. They strike the balance between column store, which I'm very familiar with, and they also supporting certain level of cubing, right? So it sounds really actually good. Actually promising. And as we drill deeper, it turned out they cannot do the device-centric computing, which is about this nested queries. So since I'm hitting a wall, try to make the cube generation faster. Then I just decided, okay, well, what if I can just generate cubes on demand? Right? I think this is what I decided coming, because I actually quite excited about that. I think that distributed SQL in my mind is a game changer, because I'm not going to see probably say 10 terabytes DRAM machines anytime soon, right? So I would say distributed memory architecture is actually here to stay with us for at least the next one decade. So I would conclude my talk with this reference. I somewhat reflect my own journey to explore solutions to the OLAP space. As a two wise men list here, like Dewitt and Stonebreak called out. And I think indexing and the highlighted features probably the amount of transactions and updates, actually those kind of stuff is actually quite essential, right? It can give me the tools and the framework to actually building OLAP solutions. Okay, I think this is the end.
You're taking questions.
Yeah.
One question I had, I didn't note it down at the time, was that 100 terabytes of data. What period of time did that cover? Is that daily rotation of data or what?
Okay. So the question is, like, what does this 100 terabytes of data cover? So in Venice, we store effectively 1 month, one rolling month. Yes. I'm just waiting for Sarah to go. Sorry, can you ask again? I'm going to repeat a question.
Basically wondering if you had any performance challenges maintaining that level of storage.
Okay, I think the question is, do I have performance challenges to maintain the level of inserts? It's kind of yes and no, because ingesting the terabytes of data is challenging. I think that's why Postgres 10 was partition, right? Because you can parallel insert into different B trees. So I think this helped a lot. And I think Citus do have other ways of doing that, but I think for my use case, because I only ingest a few terabytes for the cluster I got, so I think my dumb solutions through the coordinator and then send it to the worker nodes is actually seems to be sufficient. The challenge is actually more on the cooking side, right? So, but once with our data have ingested inside the database, and how do I, because I need to parallel cooking into those derived tables, right? I think this is because I'm using one kind of logical table, and this would having a bit of all the performance bottleneck, right? Because I think the Postgres right now does not support parallel writes into the same partition tables, right? Because I'm actually doing the bulk writes. Yes. Okay, so the question is it 4 terabytes per machine? No, because I cannot afford 4 terabytes a machine. So this is actually consists of this cluster is about 11 in Azure terminology E64 E-class machines. So each machine has 64 cores. And each machine has about given to the user or to the guest OS about 420 gigabytes. Yeah.
You started with a traditional Hadoop map cluster. What other databases did you evaluate before you picked Postgres?
Well, I actually had experience with Hive and Hadoop, but the production system is actually running internally. We call it Cosmos and the Scope system. It's kind of like a Hadoop, but I won't say it's a database system. And the other thing I look at it is I talk about I try to see if I can use Flink to solve the problem, right? Because Flink and Spark in the same family. So I have a colleague who is a Spark contributor. So I kind of pick. I say, okay, these two systems very similar. Pick one. So I picked out Flink. I said, since from my Flink experience, he can cooperate with me about if possible to do that in Spark. Yes.
You mentioned you doing some partitioning in a way that if there was corruption, you could recover by clearing the corrupted partitions. As I understood it, could you clarify what kind of corruptions you were seeing and how often, and how much you tended to lose when you recovered?
Okay, so the question is about how often do I see corruptions, and what kind of like approach I'm taking to recover see the data, right?
And also interested in what sort of corruptions you're seeing.
Oh, okay, sure. Right, it's also about the type of the corruptions. I think based on, I mean, this system been going live for about 1 year now. For the corruption I have seen is there is a table corruption. I mean, there's a table corruptions for whatever reason. The backup files associated with this table is gone. I had no idea what's going on because it could be an OS bug, could be Postgres bug, could be the underlying managed storage, right? Because I'm using quite a deep stack. So for that one is I just dropped the table, right? Because there's nothing really there anyway. So I just drop the metadata, cut by the bullet, and like re-ingest it. The other ones a little bit more common is like I see. Okay, the table corruptions happen about as once, and there's probably 5 to 6 times I see the index corruptions. So the index corruption is relatively easy to solve, but because it's kind of painful. I mean, like because it's somewhat a life-size issue. Because the recovery is also very quick. I just drop the index and recreate it. And there's other type of corruption is actually I call it our own fault. It's our own kind of user data corruption, right? Sometimes people just give me the wrong data. I just swallow poisons, right? So. Yeah. I think those things turned out to be well. There's an interesting anecdote. Is I swallowed almost 2 weeks worth of bad data. I mean, there's a column just wrong. That just gave me the wrong value, right? So I have between rock and hard place. I can drop the table. That will take me like 7 days doing nothing but to actually recover, say, the actual data. And or I decided, okay, it's Postgres. I can do updates. So I just buy the bullet. It's just, pick a weekend because its query volume is quite low. And I just wrote an update statement. So update about 26 billion rows in 10 hours, right? And I was actually quite impressed by this. And then after that, I just asked around inside Microsoft, is anyone else can do 26 billion row updates like this under 10 hours? Well, it turned out my cluster is actually the only game in town because it's do the store procedure updates, right? So in very rare occasion, I kind of use, well, turned out I have to use a hammer twice because after I got the data, because usually bad things come in pairs and people give me bad data. Then, say, a week later, find out, okay, they give me bad data again. So I have to do it. I mean, in 1 month, I have to spend, say, 20 hours to do that. And other than that, I do not really use, say, update for data recovery that often.
Follow-up question. There were some fixes to Postgres bugs that could cause index corruption a couple of years ago. I'm wondering if you know the exact version you were using, whether it would have been before or after those fixes.
Okay. The question is about about the Postgres version and some of the say corruption correlation. Well, I'm a cheapskate, so I'm actually using I started with Postgres 10, right? So I think when the Postgres 10 was released October last year, I decided, okay, you know what? I'm just going to standardize on Postgres 10. If I pick up all the fixes associated with that. I think that Postgres 10. I mean, as I said, except one, like table corruption, I have no idea. I mean,
do you know if you're using 10.0 or 10.1?
Oh, okay. So the question is which exact version of 10 I'm using. In the production cluster, I believe it's 10.4, and with Citus 7.4. I have another cluster I didn't talk about here, which is 3 times the size. I'm using, I believe, 10.5 with Citus 7.5. Yes?
Was that 6 billion rows in one transaction, one statement?
Say that again?
You said you were able to import 6 billion rows. Was that a single transaction?
Oh, Okay, the question is, I import 6 billion. I'm not sure kind of where I said about 6 billion rows.
You did an update. You did your repair.
Oh, I see. Okay.
Was that one transaction?
Okay. So the question is, did I update 6 billion rows? I actually update 26 billion rows. I would say probably not one transaction. It's about, since I'm doing the table partitions for 2 weeks, so probably I would say at least 14 transactions. Yeah, I think Citus because it's doing everything in parallel and with two-phase commit.
But one statement at the coordinate.
Yeah, one state. I mean, there's 14 logical statement, and then there's depending on the shard, there's and I think there are actually thousands of update. Yeah. Oh yes.
You use Apache Kafka for the data integration Citus, right? You then you stopped using that. So what is the tool after that?
Okay, so I think the question is, I talk about Kafka and then I stopped using Kafka, and so I actually replace the Kafka with the storage side. I'm just using Azure Blob Storage, and there is because the data integration is always involved two parties. So my upstream is actually using a service called Azure Data Factory. Right, they effectively have done is internal. This is only kind of unique to Microsoft because we have two fabric. We have internal private Azure data center. We have Azure, which is public cloud. That data factory is moving the data from the private like data center or the private fabric into the public cloud because my system is running on the public cloud. Okay, so I think the question is about how much is the buffer hit ratio, and I basically assume you're talking about the Postgres buffer hit. I think this is actually depending on the queries, and also depending on time of the day, because say as we speak now, so say Pacific time, and all Microsoft Windows engineering team is located in this time zone. But the buffer hit ratio is not very high, right? So, but during scheduled queries, it's almost like 100%. Oh, okay. What forms?
How many users are actually querying your dashboard and using them, like on a daily or monthly or whatever basis?
Okay. So the question is, how many users are querying the system? I think monthly active users, a couple thousand, because there's over 6,000 Windows engineer, and I think daily, every day, there's at least a couple hundred active users, and I think the major consumer for this system is there's a lot of dashboards. So we have hundreds of dashboards. So it's not really human. It's doing the query is actually the dashboard just refreshes. So by itself, sometimes 10 times a day. Certain dashboards are crazy. Do a refresh every 20, 25 minutes.
How hard is your coordinator and worker? Do you see rather than going to 80% CPU, which one is
Okay, so the question is about say the resource utilization on workers and edge coordinators. For my use case, I think initially the coordinator is CPU utilization is very little, and now the coordinator utilization going higher because, as you can see, to do the failure rate calculations, the hyperlock log table is hosted on the coordinator. I think even that is still using 20% of the CPU, 20 to 30% at most, because actually my coordinator is also double purpose and also as an ingester node, right? Because as I get rid of Spark cluster, I need a place to host my say ingester. So I just put the Go runtime on the master node. And sometimes I think that at peak probably it's go up to actually 60%. So as for the worker CPU, because it's actually like a database, so it's mostly I/O bound. So it's the CPU is about 30%. So at the peak, and occasionally say shoot up to say like 70%, and that's probably some other say background maintenance and work from Postgres going on, but it's actually kind of rare. But obviously on average, so it's about say 15 to 30%. It's kind of just kind of fluctuate there. Okay. Oh, okay. So how many worker nodes I have? For the current one in production, I have about 10 worker nodes and 1 coordinator. And these are fairly beefy machines. And in the one coming up, I have 3 times of the say the worker nodes. Oh, it's actually 3 times of the machines, right?
All your loads are spread across the day, or is it mainly night time? All your ingestion,
Yes.
is it happening in the night window or whole day packets?
Okay, so the question is, so is the ingestion happen at fixed time or a fixed time interval? The answer is no. I mean, this database cluster is actually very concurrent because the data can come in at any given hour, or and also the query load is happening. So constantly it's having a lot of read and write activities, and including say like vacuum happening at the background for the Postgres cluster.
What's the maximum number of rows inserted?
Oh, so the question is about how many rows has been inserted. Well, I said it's about say the data size is about 3 terabytes. At the moment, I think next month it will be actually double or triple that amount. So I would say daily, we have say 10, say around range of tens billions of rows. Okay, well, thank you very much for coming.